In this mini lecture, we'll discuss how and why atoms absorb and emit light and what this tells us about electron behavior and structure in atoms. Well before we fully understood atomic structure, scientists had figured out that light can be produced if you expose certain elements to heat, light, or electricity. In this image, electric current is passed through a tube filled with a gas. The energy in the electricity excites the atoms, leading to the emission of light, and as we can see, each element emits a specific color. This is exactly how the neon lamps typically seen in sports bars and on flashy signs produce their bright colors, and if you want to read more about this, you can go to this link below. The light from the atoms may appear one color, but when we send the light through a prism, we see that it is comprised of several sharp bands of color at very specific wavelengths. The spectra shown for helium and barium below represent what we call the atomic line spectra for these elements. The signature atomic line spectrum for each element can be used to identify the element as it is unique to each element. Here we see an example of sodium which emits only two lines close together in the visible region of the spectrum, while hydrogen has 4 emission lines in the visible region. In the late 1800s, Johann Balmer studied the atomic emission spectrum of hydrogen and discovered a mathematical model that allowed him to directly calculate the wavelengths of these 4 emission lines. In this equation, the difference between 1 over 2 squared and 1 over another whole number squared times a constant value gave the reciprocal of the wavelength. Note that the only units in this equation are inverse nanometers, and based on the algebra, this means that the equation would give a wavelength in units of nanometers. Now, based on the wavelengths given in this atomic line spectrum below, can you calculate the value of n for each of these lines? Feel free to go ahead and pause the lecture and see if you can plug in these wavelengths in nanometers that are given below and solve for what n would be for each one of these lines. Now, the atomic line spectra of hydrogen is not restricted to the visible region. Hydrogen also has emission lines in the UV and infrared regions of the electromagnetic spectrum. So it's not long before Johannes Rydberg comes along and discovers that Balmer's original equation can be modified to fit all of the emission lines in the atomic line spectrum of hydrogen. Note that the values of m and n now both represent whole number values. This final version of the equation is now dubbed the Balmer-Rydberg equation, and the constant value of 1.097 times 10 to the negative 2 inverse nanometers is now dubbed the Rydberg constant. Note again that this version of the Rydberg constant is given in inverse nanometers, which would allow calculation of the wavelength, lambda, in nanometers. However, sometimes you'll find the Rydberg constant given in inverse meters, which would then give the wavelength in meters. So pay attention to the units on the Rydberg constant when you use it in these equations. Now, if we can determine the specific wavelength at which each of these lines occurs, then we can also say something about not just the color of the light that is emitted, but the energy of the light that is emitted, as we now know how to calculate the energy of light from its wavelength. So, if each line in this atomic line spectrum represents a certain amount of energy coming from the atom, then what is going on here? Why are we seeing energy being emitted from the atoms when we are providing them with energy via electricity, heat, or light? And what is the meaning of these random whole number values, m and n, that are used in these equations? How do they relate back to the atom itself? To understand this, we must first understand how energy can be absorbed or released by atoms, and it all comes down to electrons. The electrons within an atom occupy what we call energy levels within the atom, and we'll talk about this a little bit more later. These different energy levels can be visualized as steps or rungs on a ladder, where the lowest energy level is shown at the bottom and higher energy levels are shown as we continue up the rungs on the ladder. The diagram I've showed here is called an energy level diagram and represents the electronic structure within the atom. Since this diagram starts with an electron in the lowest energy level of the atom, indicated by this small dot on the lowest rung of the ladder, we call this the ground state. Now, if the right amount of energy in the form of light, heat, or electricity hits the atom, indicated by the wavy line here, then that energy is going to be absorbed by promoting the electron from the ground state energy level to a higher energy level or rung in this energy level diagram. We call this new state an excited state. The electron does not remain for very long in this excited state, and it's only slightly stable. the electron really wants to be in the lowest energy level possible, which means it wants to return back to this ground state. So it relaxes back to the ground state by emitting the energy it had previously absorbed as light. Note that the energy difference between the two rungs shown here dictates the energy that is required or needs to be absorbed to excite the electron to the second rung. But it also dictates the energy that will be emitted when the electron relaxes from that second rung back down to the first rung. Therefore, if we know the wavelength or color of the light that is emitted, we can calculate the energy difference between the first two energy levels. Finally, note that these energy levels occur at very specific, or we sometimes say discrete energies, and therefore we say they are quantized, as each level has a specific energy and there are no other possible energy levels in between the lines we've indicated here. If enough energy is provided to the electron to promote it to a higher energy level, then it will emit a different color of light when it falls to the ground state. In these two diagrams, we see that the relaxation of the electron from the second rung to the first rung emits low energy red light, but the relaxation of an electron from the third rung to the first rung emits higher energy green light. Note that both of these two diagrams represent different excited states of the electron, and in both cases the electron is relaxing all the way back down to the lowest energy level or ground state. This now gives us the basis for understanding where these discrete lines in the atomic line spectra come from. Niels Bohr was the first to propose this energy ladder model for the electronic structure in an atom, and the first visual representation of the energy levels were as electron orbits at certain distances from the nucleus. In this animated figure on the left, we see the electron in an excited state when it's in this second orbit farthest from the nucleus. And when it jumps back down to the inner orbit, it emits energy as light. Now, once it's in that inner orbit, which we'll think of as the ground state here, and I'll wait for it to fall, note that at this point, light can come in and re-excite that electron back to the excited state, which is that further orbit from the nucleus. So the electron can go back and forth between these two states by simply emitting or absorbing energy. Now, in the model shown on the right, we see the specific relaxations for the electron in various excited states of the hydrogen atom, with each energy level indicated by these circular orbits and labeled with a value of n, where n equals 1 represents the ground state. Note how the relaxations match the line spectrum of hydrogen. When an excited electron relaxes from the third energy level to the second energy level, it emits lower energy red light of 657 nanometers, creating that line we see in the red region of the visible spectrum. But when an excited electron relaxes from the fifth energy level to the second energy level, it emits higher energy violet light of 434 nanometers, as there is a greater energy difference between the fifth and second energy levels compared to between the third and second energy levels. Also note that the electrons in this diagram are not relaxing all the way back down to the ground state, or n equals 1 energy level, so we can start to see that an electron within an atom will have many possible transitions that it can undergo within this energy ladder, and sometimes these transitions will bring the electron back all the way down to the ground state, but other times we might see the electron make more than one transition on its way back to the ground state. So for all three of the transitions indicated here that end up at the n equals 2 energy level, they would probably then go on to relax again to go down to the ground state, or n equals 1 energy level. But where does this energy difference in these orbits around the nucleus come from? Part of it has to do with the distance of the electron from the nucleus, but another thing we should consider is the wave-like properties of the electron. Not all waves are traveling waves like we've seen in previous animations, which can take on any value for wavelength or frequency. Some waves are stationary, and their oscillations must occur between two fixed points. This fixed distance is going to set the specific wavelengths that are possible, because the standing waves that occur have to have specific segments that oscillate. So these standing waves and these possible wavelengths that occur between this fixed distance will be quantized, as we can see in this image, meaning that they have a specific number of segments and therefore a specific distance between the different points that are indicated along these pictures. Now, common demonstrations of a standing wave are usually done with a jump rope held by two people at opposite ends. I've tried to replicate this here with this animation. One person on one end of the rope moves their end rapidly up and down until a harmonic oscillation occurs between the 2 points. Here we see the first stable oscillation being reached when the oscillation reaches its maximum at the top and bottom. As they oscillate the rope faster and faster, it becomes broken into more and more segments that are oscillating with a fixed point in between them. Here we see the second stable oscillation with one relatively fixed point or node in the middle with oscillating segments on either side. Now, at no point will a stable oscillation occur that only contains part of one of these oscillating segments. You always have to have a complete segment that's oscillating up and down. So for the next stable oscillation, we add another oscillating segment and now have 2 nodes. And then for the next stable oscillation, we add another oscillating segment, giving 3 nodes. To think about how these standing waves occur in an orbit around the nucleus, we need to connect the 2 fixed ends of the standing wave to make a circle. Then the n value for the energy levels represents the number of oscillating segments occurring within the diameter of the orbit, and mismatches for these oscillations are not allowed. Here are some animations that may help visualize these standing waves for particular energy levels. In the top right, we see the standing wave for the 3rd energy level, and on the bottom, we see 2 different views of the standing wave for the 8th energy level, one from a top-down view and one from a side view. So, Bohr comes to some conclusions about the electronic structure in the hydrogen atom. First, that the hydrogen atom has only certain allowable energy levels indicated by the value of n in this equation. He determines this equation that gives the discrete energy of these energy levels, with another constant being included, k. He also proposes that the energy levels are associated with fixed circular orbits around the nucleus, as we have just seen can be explained by the need for a stable oscillating pattern for the standing wave. He also proposes that a moving electron in an orbit around the nucleus does not radiate energy while it is moving, which goes against classical physics. And he proposes that electrons change their energy when they jump to other energy levels by absorbing or emitting photons. Finally, his model becomes the basis for how we understand the energy level diagram shown previously and how energy absorbed or emitted by the photons matches the energy difference between the 2 energy levels. Bohr's model becomes accepted because it helps explain the experimentally derived Balmer-Rydberg equation, and Bohr is also able to use this model to calculate a theoretical value for the Rydberg constant that had excellent agreement with the experimentally determined value set by Rydberg from his study of the hydrogen atomic line spectrum. And it's always good when a modeled value matches an experimentally determined value. Finally, Bohr extends the Balmer-Rydberg equation to give an equation that allows calculation of the energy difference in electronic transition instead of just the wavelength. Bohr also extends his model to other hydrogen-like single electron ions of the first few elements in the periodic table and determines a mathematical relationship between the energy level n and the radius of the orbit r. The positive correlation between the energy level and the radius of the orbit shows that at higher energy levels we expect to see the electron at a greater distance from the nucleus, which explains that picture of the energy levels as these orbits with increasing diameters. Finally, we should note that this model of the electronic structure gives energy levels that get closer and closer together the higher you go up the energy ladder. Note here that the biggest difference in energy between 2 successive energy levels is between the first and second energy level. The difference between the 2nd and 3rd energy level is smaller, and each successive step up the ladder has a smaller difference between the energy levels. Also note that this highest energy level, which we call n equals infinity, has an energy of 0, and that all other energy levels are given negative energies. The infinity energy level actually represents the point at which the electron would be ejected from the atom. So in the previous mini lecture, when we saw electrons being ejected from metal atoms during the photoelectric effect, this was due to enough energy being provided to excite an electron past the n equals infinity energy level, thereby separating it from the electronic structure of the atom and breaking the attraction the electron feels for the protons in the nucleus of the atom. This concludes the 3rd mini lecture for chapter 4. Please note any questions you may have and post them on Piazza.